Now, in order to find power series representation for more functions, we're going to look at how to multiply power series when they are absolutely convergent. So let's take, to simplify, two power series that are centered at 0, one with radius of convergence R1, the other one with radius of convergence R2. And so when they're both absolutely convergent, in other words, when x in absolute value is less than the minimum of the two radii, we would like to know if we can represent the product of our two power series as a power series centered at 0. So let's look at an example to try to see what we could do. We're not going to prove the result that we're going to give here, but we should see from this example that it is a reasonable thing to believe. So let's say we are looking at the product of the power series, that is the sum of the geometric series of common ratio x starting at 1. In other words, the series from 0 to infinity of x to the n that we multiply by the series from 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. It is easy to see that the second series has radius of convergence 1 as well, and therefore if we are under the condition that the absolute value of x is strictly less than 1, both series are absolutely convergent, and we would like to know whether we can represent that as a power series. Well, we can certainly look at the first few terms for both series. So we have the first series that starts with 1 plus x squared plus x cubed and so on. And the second series that starts with when n is 0, negative 1 to the n is 1. And then we have x to the 1 divided by 1, so just x. Then the next term is negative x squared over 2 plus x cubed over 3 and so on. And we're multiplying these two power series. Of course, these are infinite sums, so the fact that we can distribute is not clear, but let's admit we can, and we're looking at multiplying things through formally without caring too much about convergence and whether we can do that for infinite sums. So if we do it formally, we can look at the term of each degree. So if we start multiplying things through, I multiply 1 by x, it's going to give me just x, and in particular it doesn't look like there is any way to get a constant. You have 1 by x is already of degree 1, and then if you multiply 1 by any of the other terms you get higher degrees. And of course, if on the left hand side I multiply by x instead of 1, I'm going to get even higher degrees. So that means there is no constant term. Then we can look at the terms of degree 1. So what is the coefficient of x? Well, we have x multiplied by 1. And then if I multiply by anything of higher degree on the right hand side, I get something of degree higher than 1. And on the other hand, if I multiply by something else than 1 on the left hand side, then I'm going to get degree at least 2, like here, x by x. So the only way to get x is 1 multiplied by x, so we get just x. Then we can look at the terms that give us x squared. So we have 1 multiplied by negative x squared over 2, that gives me negative 1/2 times x squared. And another way to get x squared is to multiply x by x. So that gives me 1 minus 1/2, all of this multiplied by x squared. And you see that any other combination is going to result in something of degree higher than 2. So for x squared we have just 1 minus 1/2, in other words 1/2 for the coefficient. And what about x cubed? How can we get x cubed? Well, we can get x times negative x squared over 2. That's going to give us negative 1/2 x cubed. Another way to do it is x squared times x. That's going to give us 1. And the third way to do it is 1 multiplied by x cubed over 3. That's going to give us 1/3. And you see that any other combination is going to result in something of degree higher than 3. So this is it for x cubed. Now here you see for the last one for x cubed, you get the idea of what we do. You're looking at all the combinations that result in something of total degree 3, which means that to do that you can take degree 0 on one side and degree 3 on the other, or degree 1 on one side and degree 2 on the other, or degree 2 on one side, 1 on the other, or degree 3 on one side and 0 on the other. So that means that to find the coefficient for a given degree, we're going to have to run through all the possible products where the total degree adds up to that particular degree, and add things up. So in this case, we end up with the first few coefficients, x plus x squared over 2 plus 5/6 of x cubed, and so on. And practically speaking, even though we're going to give a general result for the form of the power series representation of the product, we're going to, practically speaking, usually just calculate the first few terms, and for many applications this will be good enough. So the theorem is this, and here of course we admit that if we have two power series that are absolutely convergent for absolute value of x less than r, then we can represent this product of the two power series as a power series centered at 0 that converges absolutely for absolute value of x less than r, and the way you get the coefficient is doing exactly what we did formally in the previous example, which is running through all the combinations of coefficients that are going to give you a total power n for x. Right? In other words, if on one side you take ak x to the k, and you want the product with a term on the other side to add up to x to the n, so you have ak x to the k, you will have to multiply by the term multiplied by x to the n minus k, so that when you multiply through you get x to the n. So you have to multiply ak by b indexed by n minus k, and do that for all the possibilities, which means that k is going to run from 0 to n. This is pretty much the process that we've described in the previous example. So with these coefficients, we obtain a power series of coefficient Cn that represents the product of the two power series. So how do we use these kind of things? Well, for instance, we can use it to evaluate limits. Let's say we want to evaluate the limit as x is approaching 0 of 1 plus x minus e to the x multiplied by sine x divided by cosine x minus 1 plus x squared over 2. If you plug x equals 0 at the top, you get 1 plus 0 minus e to the 0, which is 1, so that's 0. That you multiply by sine 0, which is also 0. And at the bottom you have cosine 0, which is 1, minus 1, that's 0, plus 0. So you have an indeterminate form of the type 0 over 0. And of course you could use the rule of de L'Hopital. And I encourage you to try. You will find that you will have to iterate this process a number of times, and that handling the derivatives becomes cumbersome because at the top you have a product. So with the product rule, when you apply the product rule repetitively, then you get you get more and more terms, and it gets cumbersome to keep track of everything. It is certainly possible, but not a very pleasant process. An alternative here is to use our knowledge of power series. At the top we have this one factor that is 1 plus x minus e to the x, and because we know the power series representation for e to the x, that is valid for all x, it's 1 plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4 factorial and so on. This 1 plus x minus e to the x can be represented by the power series negative x squared over 2 minus x cubed over 6 minus x to the 4th over 4 factorial and so on. On the other hand, sine x as a power series representation that starts with x minus x cubed over 6 plus x to the 5th over 5 factorial and so on. And at the bottom, we can also write out a power series representation for the bottom, because cosine x has also a power series representation valid for all x, just like for sine x. And it starts with 1 minus x squared over 2, and then the next term is x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So we can write cosine x minus 1 plus x squared over 2 as x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And we're going to divide the product of 1 plus x minus e to the x with sine x by this term that we have at the very bottom. And you see that in the power series representation of this term at the bottom, the first non-zero term is x to the 4th over 4 factorial. So we're going to have something that goes to 0 like x to the 4th multiplied by some constant. So that will be something to keep in mind to see how many terms we need to calculate for the product. So if I look at the product of 1 plus x minus e to the x times sine x, the term of smallest possible degree is going to be negative x squared over 2 times x, and that's going to give me negative x cubed over 2. And then if I multiply this negative x squared over 2 by the next term in sine x, I already get something of degree 5. If I multiply negative x cubed over 6, the next term in 1 plus x minus e to the x, by the first term in sine x, I get something of degree 4. And then the next term will be again x to the 4th times x, so of degree 5. So if I just write out the first two terms, I'll have just the degree of degree 3, the term of degree 3, which is negative x cubed over 2. I can only obtain x cubed by multiplying negative x squared over 2 by x. And the only way to get something of degree 4 is multiplying this negative x cubed over 6 by x. So I get negative x to the 4th over 6. And then I have two ways to get something of degree 5, but I'm not even going to bother because I know that I'm going to divide this expression by something that starts with something of degree 4, and you will see that what we have is good enough to conclude, because now if I write out my quotient, what I have at the top, the product that I have at the top, I know that I can factor out x cubed, and then I get the constant negative 1/2 plus a bunch of terms that are going to contain, it doesn't really matter what it is, all I know is that each of the complementary terms is going to contain a positive power of x, so that when we look at the limit for x equals 0, these terms are going to go to 0. At the bottom I can factor x to the 4th, and then I have a constant, namely 1 over 4 factorial, plus a bunch of terms that again contain a positive power of x and are going to go to 0 as x goes to 0. So now if you look at what we have here, x cubed over x to the 4th, we can cancel out x cubed. We have 1 over x multiplied by something that is going to go to some constant, right? Taking into account that all of the complementary terms are going to go to 0. So we have 1 over x multiplied by a negative constant, negative 1/2 over 1 over 4 factorial. And so it's going to behave as x goes to 0, just like 1 over x multiplied by this negative constant. So we're going to get an infinite limit as x goes to 0, because 1 over x goes to infinity. And specifically, if we're approaching 0 from the right, then 1 over x is positive. We multiply is positive and very large as we get close to 0 from the right. And we multiply by a negative constant, so we're going to get negative infinity for the limit. If we were approaching from the left, then 1 over x would approach negative infinity. We multiply by a negative constant, we would get positive infinity. Now turn to the next video where we're going to discuss binomial series.